Oh, I see that. Yeah, I do see that. No, like the analysis. No, I think but we finished like our
Let's see here. Golly, where is everybody? Are people gone for break already? Yeah. Mentally, yeah. All right, let's see here. Sarah B, Claire, Matt, Luke. Oh, Sarah B, there you are. Jaden, Emma, Liza, Stuart, Ethan, Manya, Olivia. Let's see here. Kashal, Diego, Darwin, Sean, there he is. Jules, Doa, Matthew, perfect timing. You're Matthew R, right?
Yeah.
Okay. Colin, I saw Colin before. Is he? Surely he's coming back. I'm going to mark him down. Emily, Rennick. He's coming back? Okay. Sarah T. McKenna. Is there anybody here whose name I didn't call? Oh, yeah. Luke? Okay. All right. Kashal? Okay. Okay, time to get started. Okay, so last time we were talking about change of variables, and remember, change of variables is a way to, it's kind of like substitution rule, except our primary motivation is not to change the integrand. Rather, our primary motivation is to change the domain. Because domains are a bummer, right? When you're doing double integrals, I mean, you take a domain like this, this thing right here, I mean, slicing this up, you're going to hit corners there and there, whichever way you slice, and that's going to be super inconvenient. Nobody wants that. Okay. All right, so changing a domain perhaps to something like that, that's the dream, right? To get a rectangle, that's the best case. Highly desirable. Okay, so we talked through most of this example last time, but let me remind you of the highlights. The big idea is that sometimes your change of variables function that's easiest to write down is actually going the wrong way. As it were, it's not going the direction we would like. In other words, I don't want to pull back through that, right? I want to pull back through a function that goes that way, so that pulling back will give me the new domain that I want. Okay, so this function is going the wrong way. That said, this function is really easy to write down. It's really easy to motivate. Yes, question. Well, so yeah, so this function as it's written here, X and Y are what go into this function. X and Y are the inputs, right? And so this is what goes in, and then what comes out are U and V, and so these are the outputs. So
going the other way, would that be like X equals U plus
yeah,
V or something?
if X and Y were functions of U and V, which is what we've done in the previous examples.
Right.
You know, yeah, here X and Y were functions of U and V. That's right. Yeah. So right. So where does this change of variables function come from? It comes from a real clever trick. If you can find a way to write your bounds, you know, all the equations that you're given that bound your region, if you can write it as stuff that equals constants, right? So this thing called xy, right? That's equal to a constant there and there. And then there's xy squared. That's equal to a constant on the other two edges. That gives you two functions, which together, let's see here, I'll use this color. That defines, well, I'll do it like this. That defines a function that goes this way. And what's nice about this particular trick, if you make this choice, looking at what's constant, the edges turn out to be straight lines, right? So this curve here, for example, xy equals 1. Okay, well, yeah, but xy is u, so that's just the edge u equals 1, which is straight up and down, part of a rectangle, and again, we win. Okay, so that's the big trick. By the way, FYI, it will not always come at you in this convenient format that I gave it to you. I mean, I already gave it to you in the form that the equations were stuff equals constant, right? So you might have to do just a little bit of algebraic work to get there. So for example, maybe this might have come at you as y equals 1 over x. Oh, whoops. And if that's the case, then okay, then rewrite it as stuff equals constant, and then take it from there. Okay. Okie dokie. So I'm going to compute this determinant right here. Partial UV, partial XY. Now, why am I computing that one? Because that's all I have, right? I know formulas for U and V in terms of X and Y. And so if I'm going to take partials, all I can take partials of are U and V. I don't know what X is. I don't know what Y is. Side note, not that we couldn't solve for them in this case. Yeah, of course we could in this case, but there are cases when you can't. And for whatever it's worth, even here when you can, it's easier not to. Right? So I know U and V as functions of X and Y, so let's take the partials in that direction. And that gives me, this thing that, well, at least I have. Now, is that what I need? Is this the one that I need? Well, gosh, we had to think it through. This is the integral I'm trying to compute. This is what the question asked me to do. I want to turn that into a du dv integral because I want to be in the uv plane instead of the xy plane. I'm doing a change of variables after all, right? So apparently I'm going to need to rewrite dx dy as something times du dv. And what is the thing that I will need to turn dx dy into du dv? Well, this notation, again, you kind of got to love it. I need those to cancel. Right? Again, notation crime, but I need those to cancel so that this will work out to be the way I want. Very convenient little mental trick. And this makes me realize, okay, the stretching factor I need is this. So now let's compare, right? The one that I have is partial UV, partial XY. The one that I need is partial XY, partial UV. What I need is the reciprocal of what I have. And notice the notation does all of that for me. So I don't have to, I think it's always healthy to kind of be thinking in terms of which way does the function go. And it's, visualizing, yeah, I'm doing a pullback, but which direction am I doing? That's all good and healthy, but you don't have to, because just the formulas that you have will tell you which one you can compute, right? And the formulas, with the integral that you're interested in will kind of cause you to realize which one you need. And then you can just look and see, do I have the right one or do I have the reciprocal, right? And now let's see, let me get my colors back. I have that one. I want this one, which is apparently the reciprocal of the one that I have. So I love this notation. I think it's, very handy and strongly encourage its use. Okay. All right. And then we get to this business about how do you actually You know, once you write all that down and you have yourself a new integral, this is an integral in the UV plane. Well, yeah, but how do I figure out what that integrand is? I do need to rewrite that integrand in terms of u's and v's, because I need to evaluate this integral, which is a du dv integral. Now, real quick note for your consideration, and let me zoom in so we can see better. This is a thing that I need to figure out how to rewrite. Notice I do not need to figure out how to rewrite this. Rewriting x to the 8th y cubed. I mean, yes, that was the original integrand, but it's not going to be my eventual integrand. So why are we converting something that we will eventually not care about? Don't bother, right? And likewise, the stretching factor down here, I don't need to know how to write this in terms of u's and v's. Happens to be easy in this case, but the point is I don't need that. What I need is the one that's my eventual integrand. So don't do this conversion too early in the process. You're just wasting time. Okay. So yeah, so then there's this different every time. This is by hook or by crook, all right? Make reasonable guesses. I made a guess here that since I have a product of powers of x and y, and I want to rewrite it in terms of, well, products of powers of x and y, I speculate, complete speculation, that if I take a product of powers of these products of powers, that might give me the product of powers that I'm looking for. That's just a guess. I mean, it's a pretty reasonable guess, right? I mean, that's when you take products of products, you get products. When you take powers of powers, you get powers. It seems like it ought to work. But it's going to be different when the functions are different, and you just have to look at the algebra and make your best reasonable guess. Okay. All right, and then we've already talked about the details here, and the punchline is that this integrand that we're looking at, that thing is this in terms of u and v, and then you've got an integral that you can crank out. Okie dokie, how we doing? Yes.
So then when you get that integrand, you solve the integral with that inside, is that the area of the feature?
Well, it's not the area, it's the integral that I was asked to compute, though. I was asked to compute this integral. And so, you know, why are we computing this integral? Well, it's, you know, it depends on, you know, what we're doing. But yeah, is that cool? Yeah, yeah. Anybody else? Okie dokie. So now there's this formula we've been using. Let's see, let me come back up here. Yeah, here we go. We've been using, I claimed that the thing that I got to stick in there, the stretching factor, I've been claiming that it's this thing here. Or let me do it like this. I've been claiming that it's the absolute value of the determinant of the derivative matrix. Why? Right, so I swept this under the rug before. Again, I wanted to get our hands dirty. Let's get some wins in the win column, and then we'll dig deeper. So let's do that now. And reminder of what this thing is this is the stretching factor. This is the thing that you multiply by this little piece of area, du dv, to get this little piece of area, you might say dx dy, right? So it's what I multiply by that area to get this area. So let's take a look at these pieces of area. I've got a little rectangle in blue over there, and I've got a distortion of a rectangle in orange here. And notice it looks a lot like a parallelogram, and it's not really even that surprising that it would be a parallelogram-ish. Not exactly, of course, it's slightly curved, but these pieces are really small in the limit, so you know. Okay, so let's crank that out then. Where do I get that from? Here's my initial rectangle. And here is the image, its distortion over there. And what I'm going to do is I'm just going to write down a formula for the area of the purple thing and try to figure out how that's something times the area of the blue thing. So, okay, we need to get our hands on these things. How do I describe these things? I'm going to point out that this edge vector is in the E1 direction, and its width is, the length is du because the width of the rectangle, I mean, that's the du direction. Likewise, this is that. And what can I say about this vector here? The way I want to look at this is that's what I'm going to call an output change. It's the output change associated to this input change. In other words, if I am, here and then I move to there in the inputs, that would cause me to be here and then move to approximately there in the outputs. I have an input change and I want an output change, and we know how to do that. The relationship between input changes and output changes is that the input change gets multiplied by the derivative, and that gives you your output change. So it's actually a pretty straightforward argument to figure out the formulas for these edge vectors, analogously over here, of course, to figure out those edge vector formulas. Once you've done that, well, now, I mean, I don't want to say it's all over quite, but I mean, we've got it down to some algebraic manipulations at this point, because we know how to find the areas of parallelograms. Right? The area of a parallelogram is what you get when you take those edge vectors and make them the columns of a matrix, and then take the determinant. Right? Well, the absolute value of the determinant. Oh, I keep messing up my color choices. Let me do it. I'll use yellow. So the absolute value of the determinant is how you compute area. dA. Yeah. Yeah, so now we've got this great big determinant here. How we're going to compute this thing? I'm going to observe that there's a scalar du inside of there. Du scalar, I will factor right out. Likewise, there is a scalar dv right there. Now, of course, that the du is only in the first column, the dv is only in the second column, but that's how determinants work, right? When you factor out of a single row or column, those factor outside of the determinant. And they're positive. Du and dv, of course, are positive, so I don't have to worry about the absolute values. So now we've got this thing to deal with. What is that? Oh, let me focus our attention. This matrix in here, this matrix whose first column is that formula and whose second column is that formula. Let's focus our attention on that for a second. What is this thing I have circled here? This is dg times the first standard basis vector. I claim, if you recall, multiplying by a standard basis vector gives you the corresponding column of that matrix. So this thing right here is the first column of dg. Let me say that a little bit differently. This thing that is the first column of the matrix I'm trying to understand, this thing that is my first column is the first column of dg. And then likewise over here, this thing that's the second column of the matrix I'm trying to understand, it's the second column of dg. So that's dg. It's got the exact same first column and the exact same second column. Yes.
Can you explain then why we can factor out du and dv?
Yeah, so it's a linear algebra thing. When you're taking a determinant, if you factor out a constant out of an entire column, all the elements in that column, just the column, then the determinant gets multiplied by that amount. So that's what happened here. This is a constant. This is a scalar factor in that entire column, and so it factors out of the determinant. Yeah. Right. Okay. So here's what we've got, and notice it's exactly what we needed. Let's see. I've forgotten the colors that I used, but anyway, this output area, I computed it, and it is clearly a multiple of this input area. and I can see exactly what that multiple is, and that multiple, that therefore my stretching factor, God, my elbow, this stretching factor is the absolute value of the determinant of the derivative. So as claimed. So that's all it is. All right, nice little exercise. I'm going to say likewise in R3, I'm going to really go quickly through this because it's all the same ideas. Suppose you are looking at an image of a nicer domain, and suppose you've been asked to compute an integral on this ugly domain, right? Wouldn't it be nice if we could do a pullback argument, right? Well, XYZ is G of UVW. Right, that's what G does. This is what it means to plug in. Then there's the whole business about the you know, a piece of volume over here, and how do I compute that in terms of little pieces of volume over here, and what is the stretching factor? And y'all can compute that stretching factor yourselves. And you can do it by making an argument that's morally the same as this. It would just have one extra vector, one extra sort of dimension. It'd be a parallelepiped instead of a parallelogram. There'd be 3 edge vectors instead of 2. It'd be the image of a cube instead of a square, or a rectangular box instead of just a rectangle. Right? So very, very analogous argument. I think it's a fantastic exercise. I strongly encourage everybody take the time to adapt this, make it 3-dimensional instead of 2-dimensional, and you will conclude that the stretching factor is, again, it's the absolute value of the determinant of the derivative. Same argument. Okay, and again, this notation. Yeah, I forgot my absolute values here. Shame on me. Look at this. I just totally lost those absolute values. That's my bad. So here we go. Absolute values. Sorry about that. But yeah, so this determinant, again, we write as a partial. And again, it's an abusive notation. And again, it's super convenient. All right. So I'm going to show you another example. Well, I'm going to show you a 3-dimensional example. We are going to take advantage of something that I drew your attention to last time, but I didn't actually write it down as a theorem. Here it is as a theorem. And that is that if you have a linear transformation represented by a matrix, then that matrix is also the derivative matrix. Right? And so again, this is something that you can check for yourselves. It's not that big a deal. It even, the way I've written it here, even looks more plausible. It's like I took the derivative of AX and the derivative was A. Really rolls off the tongue nicely. It's very, that's just notational familiarity, but nevertheless, it's very satisfying. But again, make sure to check it. Right? It's just a matter of writing down, just do it for 3x3 matrices, perhaps. And just, coordinate by coordinate, you can confirm that sure enough, this works. Okay, so with that in mind, suppose my domain for an integral that I'm computing is a certain parallelepiped defined by 3 edge vectors, B1, B2, and B3. So 3 edge vectors given, that makes a parallelepiped. That parallelepiped is my domain. How am I going to deal with this domain? Highly undesirable. Real quick observation. Notice if I were to try to take regular, slices, the usual slices of this thing, I mean, there's corners everywhere, right? That's nightmare. We don't want to do that. Okay. Okay, the real slick move. Again, don't think to yourself that you should have to invent this idea on your own. You don't have to invent it. You get to just hear it as I did, as the person who taught me did. right? So this is a clever idea that I don't even know who first thought of this, but it's really powerful and convenient. If you have a parallelepiped, and if you want to view that as being the image of the unit cube, all you got to do is take your three defining vectors that are given, make those the columns of a matrix, and then use that matrix to define your linear transformation. That's the move. Now I want to demonstrate to you in a moment that this has worked, but that's the trick to remember. The edge vectors make those the columns of your matrix by which you define a linear transformation. That linear transformation does what we want it to do. Now, how am I going to persuade you that it does what we want it to do? Well, I'm going to confirm just directly that this E1 edge of the unit cube, that its image is this edge of my given parallelogram. How do I know, in other words, that this goes to there? Well, follow the rules. What's the image of a vector? Well, what's the image of a standard basis vector? It's the corresponding column of the matrix, which by design, by construction, right, is what it's supposed to be. So, so this just does what I want it to do. That edge goes to this edge, and that edge goes to that edge, and oh, I have to switch colors there. This edge goes to that edge, and by linearity, everything else is going to go where we want it to go. So the unit cube's image is my parallelogram. Everybody good? Real slick move. It's a great change of variables function. Remember, finding a change of variables function sometimes is the trick, and this is a good one. Okay, so kind of all over with the shouting at this point. We have a change of variables function. We can do the pullback. Details at this point. Don't forget your stretching factor. My stretching factor, of course, is the determinant of the derivative matrix. Don't forget, though, the derivative matrix is the matrix defining the linear transformation. So, boom. Now you have to compute that determinant now, right? It's some arithmetic. Now, also, furthermore, you got to figure out what this Z is, right? The Z that comes along for the ride. Don't forget that's contained in the formula, right? So this linear transformation tells you X, Y, and Z. So we're looking for the third coordinate from this formula, and I'm going to leave it to y'all to confirm for yourselves that based on looking at the third row of the matrix gives us our formula for Z, and it's that. So I'm deliberately leaving out details. Make sure you're crisp and clear on why that's that third row is the coefficients. Linear algebra. Okay, that's all over with the shouting. Got a nice easy integral. It's an integral in the unit cube. We have an integrand, which is easy polynomial. We have this numerical factor here. Of course, it's just a number, and this is an easy integral to compute. Everybody happy? Okay, so I'm going to show you all some more change of variables functions now. In fact, they're functions that we've already seen before. In fact, we've spent a fair amount of time talking about before. We just didn't think of them at the time as being change of variables functions. And what I'm talking about is coordinate systems. Right, polar coordinates, for example. Now, remember, there's different ways to think about polar coordinates, and one way to think about polar coordinates is, and a good way, further, but one way to think about polar coordinates is to think about theta as kind of doing like this in the XY plane, right? And then to think of R as kind of shooting out of the origin at distance, or something like that from the origin. But remember, you can also think of polar coordinates as being a function, where there is in fact a world, a whole space over here, the r theta plane, right? And this function defined by those equations gives you x and y as functions of r and theta. You can think of it as a function. And what's nice about that is then it's perfectly clear, for example, that theta is free to do whatever it wants to do, right? I'm allowed to let theta be 2 pi, 4 pi, 6 pi, as many pi's as you want, knock yourself out. And it doesn't, there's nothing wrong with that. Whereas over here, you know, one could argue that it feels sort of like, well, once you've gotten to 2 pi, shouldn't you stop or something? Isn't this angle, we've already got it. And so am I allowed to go around more than that one turn? It just feels weird anyway. So point is, this is a function. It's a function that takes a 2-dimensional domain and gives you a 2-dimensional image. That's what a change of variables function is. Again, we didn't think of this way at the time, but it is a perfectly satisfactory change of variables function. I claim it's going to also be super useful. Now, since this is going to be used as a change of variables function a lot, rather than computing the stretching factor every single time we want to use it, I got to compute that stretching factor again, or that's super tedious. Let's compute it once and be done with it. And so this is how you would do it, right? You compute this determinant, and you got to do some algebra. See, yada yada yada. The algebra. That's y'all can fill in the blanks on that. It's not that bad. A little bit of a trig. And it turns out that the stretching factor on this, excuse me, the determinant in question on this is just r, which is very nice. Now, is that our stretching factor? Well, close, not quite. We got to be careful with this. The stretching factor itself, of course, is the absolute value of that determinant. So you don't want to spike the football right here and say done, right? The stretching factor is r. No, it's the absolute value of that thing. But if you choose, if you make a promise, I promise I will only choose positive values of r. That's it. Oh, well, at that point, now you're taking the absolute value of a positive number and the absolute values go away, and it's perfectly fine to think of the stretching factor as just r, right? But in order to get that happy little conclusion, you do have to make this promise and stick with it, that so that I can have the convenience of not dealing with absolute values that are super annoying, I do have to concede I am now henceforth only allowed to use positive values of r. Everybody good? Okay. Okie dokie. Very similar for cylindrical coordinates. Now, again, you can think of that as, you know, directions and, you think of it geometrically, and again, that's fine. It's good. In some circumstances, that's the way you want to do it. But you can also think of it as a function. You can think of the r theta z world over here, and et cetera, et cetera. Here's the formulas, and we've got ourselves a change of variables function. 3-dimensional change of variables. And again, I can compute this determinant. And again, it's not that bad. It's a little bit of trig. Everyone should do this once in their lives. It'll take you 2 minutes. Write that down. And again, coincidentally, I don't know, we get r. I'm going to say maybe not even all that coincidentally, right? It's kind of expected because cylindrical coordinates is pretty much polar coordinates, right? So kind of not the biggest surprise we've ever had in our lives, right? And then same deal, don't forget absolute values and all that. And so we do have to promise, if we're going to use just r as our stretching factor, we do have to promise that we will not pick any negative values of r. Okay, everybody's happy, yes? Okay. By the way, real quick side note, these are the values of r I like to pick anyway, right? I kind of get annoyed when r is negative. It just feels backwards and confusing. And so basically we have to promise to do what we were hoping to do anyway. So it's a very low cost promise. All right. Ditto spherical coordinates, right? Again, you can think of it geometrically, and very often you should. You can also, though, think of it as a function. Hey, check it out. It's a change of variables function. Hey, shouldn't we compute the stretching factor just the once so we don't have to do it over and over again? Sure. Now, again, everyone should do this once in their lives. And this one is a little sludgy. This takes a little while. But it's good. It's a good practice in dealing with determinants, and it's good practice in making sure that when there is a trig identity to be taken advantage of, that you see it and use it. I think if I remember correctly, there's 3 instances of the Pythagorean identity coming up and being awesome in this calculation. So I think everybody should do it once in their lives. So I encourage you to, it's going to probably take you, gosh, I don't know, 5 minutes, right? It's so, like I say, it's a little, it's a lot to, it's good practice in being algebraically organized and then, careful. Okay. And the answer is not analogous to polar coordinates. I mean, we got R up here. The casual, careless guess maybe would have been rho to be the stretching factor. It's not. Rho squared sine phi. And you have to memorize this. Very importantly, it's going to get used a lot. Every time you use a spherical coordinate integrals, you're going to need that, and it's important. So make sure to remember rho squared sine phi. Okay. And again, I've got an absolute value obligation that I don't want to have to deal with because absolute values are annoying, right? So how can I arrange for this thing in here to be positive so that the absolute value is not an issue? A lot of people mistakenly think, again, that, oh, it's probably just like in cylindrical coordinates where I needed R to be positive. Maybe I would need rho to be positive here, but no, not at all. Check it out. What happens if you know rho is positive? Nothing. Rho is going to get squared anyway. I don't care if rho is positive or negative. Go crazy. If you're going to use negative rhos, fine, right? What you got to watch out for, though, and make sure you don't do is don't let sine phi be negative, because it certainly can. And that would absolutely require, no pun intended, for my absolute values to kick in, right? Sorry about that. So the way we can ensure that this is positive is to make this promise that phi, we will always choose to be between 0 and pi. And then sine phi does what we want. Is that cool? Again, small cost, right? Those are my favorite values of phi anyway. So, sweet. Okay. All right, so let's see this in action. We're going to do a polar coordinates example here. So let's suppose that my region that I'm interested in doing an integral on is the first quadrant portion of the unit disk. So that's my domain for some integral. Not that we can't do this brute force, right? I mean, I could absolutely slice this up rectangularly, and et cetera. Just a circle. And so again, it's not about whether you can or can't, it's about whether you want to. And I'm going to point out that if I were to slice this rectangularly, as I kind of have drawn here, well, I'm going to need to know that the upper bound for the inner integral, and it's going to have a square root in it. You can probably see that coming. If you solve for y as a function of x, square root. And square roots in your inner bounds means you're probably going to have square roots in your outer integrand. And that is not good, right? So again, not that you can't do this, but it's highly undesirable to do this in rectangular coordinates. Okay, so let's see if we can do a change of variables. I'm going to pull back through the polar coordinates formula, polar coordinates function, and I assert, we'll check that this is true. I assert that the pullback domain is this rectangle here. Now, how do I know that this rectangle is it? And it's not that bad of an observation, really. Let's look at one sort of edge at a time. Here I've got the edge, this green edge here, that's where theta is 0 and r goes from 0 to 1. So, okay, boom, theta is 0, r goes from 0 to 1. Can I say about this edge here? Well, this is where r is fixed at 1 and theta goes from 0 to pi over 2. So r stays 1, theta ranges from 0 to pi over 2. So, right, and you can kind of continue your way around. This edge is that. And then, interestingly, this edge here, r is equal to 0 everywhere on that edge, and so that whole edge just kind of shrinks down to this single point. But still, you know, we're in business, right? I mean, the image, you can see everything inside of here. Then its image is going to be, well, everything inside of here. So as desired, my what I'm going to call undesirable domain has a highly desirable pullback. Everybody happy? Yes.
What is the horizontal line through that yellow rectangle?
Oh, I haven't gotten to that yet.
Oh.
Yeah, I'll get there. Give me a second. No worries. Okay, so I've got my pullback domain. Now I just got to kind of start plugging in. What is x squared plus y squared? How do I write that in terms of r's and thetas? Well, we already know a bunch of stuff about polar coordinates. All the algebra of polar coordinates still works. X squared plus y squared is still r squared. No problem. There's this business with the area element dx dy. Well, I've already computed my stretching factor. My stretching factor is r. Right? I notice I'm sticking to my promise. All of my r's are positive over here. So the stretching factor is just r, no absolute value required. So we're kind of in business, except for the bounds. So let's now think through the bounds. So my bounds here come from looking at my pullback domain and slicing it up. And there's no tricky curves on slicing this up. I'm just straight up going to be slicing it up as I, would any other domain. The variables aren't x and y. The variables are, r and theta, but they could be u and v, or they could be p and q. But it doesn't really matter. It's still, I'm just going to slice this thing up in the usual way. So first of all, what's the range of values of theta? Well, what do my theta slices look like? Here, I'm slicing perpendicular to the theta axis. Those are theta slices. And theta starts at 0 and ends at pi over 2. Cool. Now we fix a value of theta. There's a theta slice, so that's where this line comes from. There's a theta slice, and now on that theta slice, I want to know my range of values of r. Well, r starts there where it's clearly 0, and it ends there where it's clearly 1. So r goes from 0 to 1. It's just it's a plain old rectangular slicing of a domain. This happens to be in the r theta plane instead of the xy plane. Okay. All right, and now it's all over with the shouting. So my integrand is r cubed. The r antiderivative of r cubed is 1/4 r to the 4th, and plug in the bounds, and so it's all downhill from here. It's just plugging in the usual way. Okay. Everybody good? Yes. Oh, yeah. So this right here, I'm just invoking the stretching factor that we've already computed, right? So this r, and that comes from back here in polar coordinates. When you're using these formulas, which we are, your stretching factor is r. Yeah. No worries. Okay, heads up about one thing. There is a mistake that a lot of students make sometimes, and y'all have heard me expound on how important it is. Don't forget your stretching factor, right? When you're doing change of variables, there's a lot going on. You're trying to figure out your pullback domain, et cetera, and sometimes students just space and just forget to put their stretching factor in there. And so I've emphasized that students should make sure that don't forget to put that stretching factor in there, right? And they do that first, and they're so focused then on that as having been done that they think that's their integrand, right? Which is morally equivalent then effectively to having forgotten their stretching factor, right? So don't make that mistake. The thing that came from the original integrand, that's not your integrand. That's most of your integrand, right? But don't forget the stretching factor is there also. That is part of your integrand. So don't forget that, and don't just kind of put it in there and forget about it. It is part of what you have to deal with. Okay, now there's a really nice geometric observation I'm going to make at this point that's going to save us tons of trouble. And that is to point out that we can see theta slices and R slices in the XY plane, right? So looking over here in the XY plane, I can totally see what they look like. And in particular, here are theta slices. Oh, well, let me start down here. What is this right here? That theta slice. Well, theta is a constant, and R is kind of increasing, right? So that's that. And this theta slice is that. And this theta slice is that. And this theta slice is that. And you see the pattern, right? So my process of doing theta slices, yeah, I mean, fair. If I could do that over here, and arguably, naturally, maybe this is kind of where the theta slices are happening. But really, all I need to do is to understand them. And those theta slices, well, I can understand them over here because that's what they look like in the XY plane. And then you can play the same game with R slices, right? An R slice perpendicular to the R axis. These lines are just where R is a constant. That's what they are, and R being a constant in the XY plane looks like that. So as you're doing what we did up here, right? When we had our pullback domain here, and we pulled back, and then I started doing, I was looking at theta slices of my pullback domain. I don't really have to think of, or I certainly don't have to draw, but I don't even really have to think of those slices over here. I can think of them over here. And I can think of it as that, here's my low edge. We know that low edge is there. Here's my sort of top edge. We know that top edge is really that. And so instead of thinking as, I got a slice from, blue to purple over there, I could think of it as, I got a slice from blue to purple over there. Same. And then on a particular theta slice, I mean, you can think of R as starting there and going over to there, but I can see that over here too. R starting at 0 and then moving out to whatever that edge is. Okay, I can see it right there. So here's what's wonderful about this observation. Yes, we are doing a pullback, but I don't even have to draw the pullback. Everything I need to know about the pullback, I can see right here just by understanding what slices look like in the XY plane. So here is that question that we looked at a minute ago, the one we just kind of redid. And for dramatic purposes, you see that I have crossed out All that pullback nonsense. That's the wrong word. All that very valuable pullback construction, right? But we don't have to look at it. Don't even look at it, right? This integral that I'm computing here, I can, everything I need to know about what's happening in the pullback, I can get from looking at the original domain itself. And just thinking about how slicing works in this world. So theta. All right, well, my theta slices start at 0, end at pi over 2. So my theta bounds are 0 to pi over 2. Don't have to draw the pullback at all. In fact, here's the funny thing about it. I mean, if you are going to do it this way, and by the way, this is what people do, right? Nobody draws the pullback. If you're doing it that way, one could be forgiven for forgetting that you're actually even doing a change of variables, right? When you're doing a change of variables, drawing the pullback is that's one of the visual giveaways. We're not even going to do that. Computing the stretching factor is another one of the big giveaways. We're not going to do that either. We've got that memorized. So it almost looks like you're not doing a change of variables. Now, side note, you are, and so I think it's important to view it that way. But it just kind of feels like we're just writing an integral in a different form. And so think of it less as that's confusing and more as that's super convenient. Okay, so all right, let's see another example. Oh, we have 25 seconds. I'm sure I owe y'all 25 seconds. We'll call it a day right there. We'll pick up here next time on Friday. Hope to see y'all on Friday. I know it's the Friday before spring break, but hope to see you. All right, have a good one. Yep, sure thing.